Well, good afternoon, everyone, and welcome to today's live astronomy program. My name is Justin. I'm one of the astronomers here at the Science Museum of Virginia, and I'm happy to be with you today, bringing you a little bit of outer space without having you leave your place. If you've watched any of our previous episodes, welcome back. Have another fun show for you today, at least I think so. If this is your first time tuning in, welcome to the show. We've done a couple dozen of these now over the last several months. You don't have to watch the others to enjoy today. If you want to catch up, we've got them all archived right here on Facebook. You can check out our YouTube channel as well. I also want to thank our sponsors for the series, Allianz Partners. Always great to have them on board. Thank you for your support. Now, today's show, like all of the previous shows, we're going to use the same software that we use up in the dome here at the Science Museum. It's planetarium software called Digistar. We're using Digistar 7 for today's show, and it can do some pretty cool stuff. So I recommend, if you're able to, watch this full screen on a nice big monitor if you have it. In fact, I'm going to get it switched over to the Digistar view, see what is in store for us today. Here we go. Now, just in case you didn't catch the last broadcast, it was, mid-December. It was 3 weeks ago. And one thing I wanted to do was get you ready for some things happening on December 21st. First, we had that great conjunction between Jupiter and Saturn. The closest those planets will appear in the sky until the year 2080. So I hope you're able to get out and see it a few weeks ago. See, December 21st was also the solstice. For us here in the northern hemisphere, it was the winter solstice. So I'm showing you the Earth in its present orientation. I've got the sun kind of off to the left here, and I've added the poles of the Earth, the north and south pole, so that you can see that the northern hemisphere of the planet is angled away from the sun these days. That's why the sun isn't up in the sky very long during the winter for us here in the northern hemisphere. The sunlight is less direct. The sun's low in the sky. That brings us shorter periods of less direct sunlight, lower temperatures. Yeah, it's winter out there. You probably noticed. So we marked that since my last show. Let's see, we had the New Year's holiday. So we've turned a new page on the calendar. It is now 2021. And then there was another special day that you may have overlooked it just a little bit. It was January 2nd of this year. The Earth was at perihelion. That's kind of a fun word, but what is perihelion? Well, perihelion is our closest approach to the sun for the year. If I back away a little bit here, we'll add the orbit of the Earth to the screen. And although it's going to look fairly round, the orbit of the Earth is not a perfect circle. No planet orbits the sun in a perfect circle. That's pretty hard to do, although the planets are pretty close. We call the shape of an orbit in astronomy an ellipse. That's just the way gravity works. It makes things move in ellipses. I can show you how different our orbit is from a circle, actually adding a circle to the solar system here at Earth's average distance. It's about 93 million miles. You may have heard me call it an astronomical unit in the past. So that red line, that represents a perfect circle. There's always one astronomical unit from the sun, and that blue line is the Earth's orbit. So not quite a perfectly circular shape. How different is our orbit from a circle? Well, mathematically, you can use a number called the eccentricity to figure that out. But what I'll do is just compare it to something that's a little easier to wrap our mind around. We've got the Earth there on the left, just over my head. We've got the orbit of the moon around the Earth. Now, of course, that's not a perfect circle either, but we can use the moon's average distance from the Earth to define something called the lunar distance. It's kind of intuitive. It's a little under 250,000 miles. And right now, about a week after perihelion, we are 1, 2, 3, 4, 5, about 6.5 lunar distances closer to the sun than we are on average throughout the year. So about 3.5 million miles. It's not a huge difference compared to that 93 million mile average distance, but it's worth noting. So perihelion, a good day to know. If you look forward through the year, about 6 months, it'll be, I believe, July 5th of this year. We get to the other side of our orbit, so the Earth orbiting around the sun. And in July, summer here in the northern hemisphere, we are actually a little farther from the sun on average. And July 7th this year will be aphelion, our greatest distance from the sun. That again, about 1, 2, 3, 4, 5, 6.5 lunar distances. Our orbit fairly symmetrical in that sense. That's kind of nice. And once you know what those words mean, it's also kind of nice because you can apply this knowledge all throughout the solar system. I'm using perihelion and aphelion to describe our orbit because we go around the sun. These words come from ancient Greek roots, peri meaning close, apo meaning far, and then we're in orbit around the sun, so we use the Greek name for the sun, Helios, drop the O from aphelion to make it look nicer, and then perihelion, our closest approach, what we just marked last weekend. Now, if you don't go around the sun, you can give different names to the extremes of your orbit. The moon in orbit around the Earth has an apogee and a perigee. You may have heard those words before. The artificial satellites we launch up into space have apogees and perigees as well. If you go around some other planet, you could give a special word to the extremes of those orbits. Apogee and perigee, for example, if you're in orbit around Jupiter. If maybe you're thinking of an exoplanet orbiting some other star, you might hear the words apastron or periastron. Or there are some other more kind of generic or general terms that might get used as well, probably a pericenter or apocenter are what I see the most. So kind of good information to have for you here. But how do the extremes of different orbits differ from each other? Well, the Earth, you just saw our orbit, fairly circular. Let's see if I can find the inner solar system for you. Get us pointed more towards the sun because I want to show you the orbit of the Parker Solar Probe. Let's see. I have to rotate a little bit more so you can actually see it. We'll back up a little bit too. Now, the Parker Solar Probe is in orbit around the sun. So just like the Earth, we can describe its orbit by its perihelion and its aphelion. But you can see here that as we traced its trajectory with that orange line, its perihelion is very close to the sun. It's inside the orbit of Mercury. And then it wanders outside the orbit of Venus at its aphelion. This extremely eccentric or extremely extended orbit allows it its closest approach to study the inside of the sun's upper atmosphere, a layer called the corona. Mentioned that a little bit in an episode way back in the middle of the summer, so we can find that in the archives if you like. Now, the Parker Solar Probe is going to make its next perihelion passage in about a week and a half, mid-January. So you'll see more information about Parker Solar Probe if you watch any of the space news. Another mission with a more extreme orbit than the Earth's is the Juno spacecraft. Now, Juno is in orbit around Jupiter, not the sun. So we call the extremes of its orbit apogee and perigee. And at the very end of 2020, Juno experienced its 31st perigee of its mission. It should swoop into view here in just a second. Now, just like Parker Solar Probe's orbit around the sun, the orbit of Juno around Jupiter is very eccentric. It's very extended, so it makes these very close approaches to the planet. This has a couple of advantages for both of these spacecraft. Spending too much time to their primary target, close to their primary target, is a little bit dangerous. It's really hot, close to the sun, and Jupiter here has a very strong magnetic field that traps a lot of charged particles, radiation in the neighborhood of the planet, so the spacecraft can't spend a lot of time in that intense radiation. So it has this highly extended orbit, so it just makes the occasional close pass by the planet, trains all of its scientific instruments on Jupiter, studies its magnetic and gravitational fields to help us map the inside of the planet, figure out this planet's structure. Pretty cool stuff. Now, the Juno mission was originally scheduled to end this summer, but announced just a couple hours ago, NASA has approved an extension to Juno's mission. It may last up to another, I believe it's going to be extended to 2025 if the mission, if the spacecraft remains operational that long. This will be pretty exciting because it will continue to study Jupiter. This will also allow it to make some close flybys of some of the moons that you see there. Those three inner moons, Io, Europa, Ganymede, going to get some close views of those moons as well. So a little bonus from the Juno mission. If you want to read more about that, as well as another mission, InSight, that got extended today, we'll have more information in the comments for you. If you have questions about that or anything that pops up during the show, or if you have ideas for future shows, feel free to leave those in the comments as well. But I'm not quite done today. All this talk about special points in an orbit, celebrating New Year, celebrating the solstice, the start of a new season, got me thinking about time and how we measure time. It's pretty easy today. You look down the corner of your computer screen, check your phone, you might wear a watch, probably have clocks all over the house on all your devices. But how did we originally measure time? Well, of course, the things we saw in the sky were one of the first indicators that time was passing around us. So let's take a look at some of those things and how they relate to our current measurements of time. We start a new year. We know about 365 days, but we'll start at the beginning. How long is a day? Well, there are a couple of ways you could measure a day if you didn't have a watch or a phone handy. You could just watch the sun as it moved through the sky. You could say, wait for it to reach its highest point in the sky at midday, and then use something to measure how much time had passed until it returns to that exact same point, its highest point in the sky at midday. Now, if you do this, you actually find that over the course of the year, the length of the day varies just a little bit. It's a few minutes here and there. The total range is about 30 minutes. Now, this is because of a couple of things we've already seen. The eccentricity of Earth's orbit, the tilt of Earth's axis, and so these changes are predictable. They're all described by something called the equation of time, which is maybe a little more mundane than it sounds. But no, on average, if you averaged out over the entire year, a day is 24 hours long. No big surprise there. But there are other ways you could measure the length of a day. Maybe the sun, not really your thing. You want to go out at night, check out those more distant stars. Well, if you pick a star out in the nighttime sky, measure its position very precisely, and then go out the next night, observe it from the same location, see how long it takes to return to exactly the same point in the sky, basically what we were waiting for the sun to do, you're going to find that the length of the day is just a little bit different. It's more consistent, but it's different. So if you measure a day by the sun, you're going to get 24 hours on average through the year. By the stars, you count it to be about 23 hours, 56 minutes, and 4 seconds. Interesting. So if you want to make sense of your timekeeping device, have the nighttime always be dark. As you go through long periods of time, years and decades, you've got to account for that extra 4 minutes. Interesting. That's a little puzzle. We'll save that for later. Since not even the sun and stars agree, maybe there's some other object we could use to measure the passage of time. This isn't great for days, but how about measuring months with the moon? And that's where the word month comes from. It's by measuring the position of the moon in the sky. It's on your screen there, but let's zoom in just a little bit. And we've already seen that the moon goes around the Earth. We know its orbit is not perfectly circular, but you can trace its path through the sky, and you find that, well, after a certain amount of time, the moon returns to roughly the same point in the sky. It won't be exactly where it was 1 month ago, but it'll be pretty close. So you could use something like that to measure a period of time. But there are some difficulties. The moon doesn't always go exactly to the same place for a couple of reasons. Well, first, there's that orbit around the Earth, and as I already mentioned, it's not circular. It's an ellipse. So as you see it on your screen now in this kind of time-lapse view of the moon over long periods of time, it's growing and shrinking on the screen. That's because in an elliptical orbit, sometimes you're at apogee, sometimes you're at perigee, so the distance is changing. You might also notice the moon kind of wobbling side to side on the screen a little bit too. That's because its axis of rotation is a little bit tilted compared to its orbit as well, just like the Earth's is, giving us our seasons. And then, of course, you see the phases of the moon. That's pretty obvious. As the moon goes around the Earth, the angle between the moon and sun in the sky changes, giving us those changing phases from crescents, a quarter to a gibbous to a full moon, and back again. So actually a few ways we could measure how long it takes the moon to move through one cycle. We could simply use its orbital period. We could measure its position in the sky relative to the stars. Let's see if I exaggerate things on the screen. Down towards the bottom, there's the moon. Outside its orbit, I see two stars, kind of on either side of the moon. And I've got the date down there, so we can track how long it takes. If we run time forward, how long does it take for the moon to get back to the same place compared to the stars? So right between those two stars again, that was 1, 2, 3. Okay, I've got it. I know how long it was. But let's see. There's another way we could measure the rotational or the orbital period of the moon. We could use those phases. That's perhaps a little easier to see, a little bit easier for the human eye to track. So I'm going to go ahead and change time slightly just to get the moon into an easy to recognize phase. I'm going to use a new moon. So we're going to get lined up with the sun. I'll let you see where the sunlight is coming from. I'll actually lock the sun to the right side of the screen for you. So we've got the Earth in the center of the screen, moon off to the right, sun way off to the right. Now let's see how long it takes for the moon to get back to that same position. How long does it take for another new moon to occur? Got the calendar date down there at the bottom again. Okay, I think that was a little bit longer. In fact, as I counted it, relative to the stars, 1 month or one orbital period of the moon is a little over 27 days. If we just watch the phases instead, because the moon is also being carried around the solar system by the Earth, we're looking at about 29.5 days for that cycle to repeat. Now, for cultures that use lunar calendars, they tend to prefer the 29.5-day period to approximate a year, the seasons you experience here on Earth. You take 12 of those lunar periods, gives you 354 days. Not bad, not exactly the same length of the year as we experience it here on Earth with our 4 seasons. And of course, that period of about 365 days that we just completed about 8 days ago, and that we track usually using the sun. So how did we come to this determination that a year was 365 days long? Well, let's use the sun as our guide. Though you can also do some fancy math, pretend you are the sun and figure out how long it takes the Earth to orbit around you. But we'll do it this way because this is the way the sky looked to people living on the Earth. I've marked the sun's position amongst the stars as it appeared wherever our clock was set there. It's in the constellation Pisces. I just want that there so we know where it is when it returns to the same place. Now really, this is a little bit of a strange way to show it to you. I've got the Earth stationary there. We're really seeing the Earth rotate. Looks like the sun is moving among the stars. Of course, for a reference frame here in the solar system, we think of the sun as stationary, the planets moving around it. But because our bodies are attuned to experience accelerations, changes in speed, changes in velocity as motion, and because the Earth rotates at basically a constant speed on human timescales, we don't feel the Earth moving. So we're just kind of riding around on the surface of the Earth. It looks like everything is moving around us. So over the course of the year, it does look like the sun moves compared to the background stars. And how long does it take to get back to exactly the point where it started? Well, we started on March 13th. It's March 13th again. But if we look closely, it didn't return to exactly the same point. I promise we were centered on the red X before. Now we're a little bit off center. I want to get it centered on the X again, so I'm going to add just a little more time. It works out to about 6 more hours. And now the sun is exactly where it started when I started this segment. We've advanced exactly 1 year, or 365.25 days. That's interesting. And it works out that way whether you you measure where the Earth is compared to the stars, or you measure where the sun is compared to the stars. You're going to get a little bit of extra time for Earth to complete one orbit. So if you want to make a working calendar, you not only have to worry about the mismatch between the seasons and the amount of time in the months, you have to worry about the difference in different ways to measure the day. You've really got to take account of that extra quarter of a day every orbit. If you don't do that, eventually you're celebrating your various winter harvest festivals in the middle of the summer. It's not very convenient. That's why every 4 years or so we add an extra day to the calendar. We've got leap years, and if 2020 felt just a little bit longer to you, that's because it was a leap year. There were 366 days in 2020. That's probably the only reason it felt a little bit longer. But that's just accounting for that little bit of extra that would be strange to take account for every single year. So that's just making our experience here on Earth, our calendars here on Earth, match up with the cycles in the sky, the cycles in the universe around us, helping us continue to experience things the way we're used to, making our seasons line up with what we see in the sky. So there you go. I hope you enjoyed that quick little primer on how we've measured time using different objects in the sky. I'll be back with you in about half a lunar cycle. See you in a fortnight. Got a special word for that too. I'll be back on January 22nd, and planning to revisit some of these spacecraft that blazed trails through the solar system. We've got Juno hanging out at Jupiter today, in part because some of the Pioneer and Voyager missions paved the way to the outer solar system for them. So we'll talk about that and a whole lot more in the next show. And that again, January 22nd, 3:30 Eastern Time once again. Hope you're able to tune in next time. Hope you enjoyed today's show, and I hope to see you next time. Until then, stay safe out there and keep looking up.